Welcome to More Learn, More Teach, where I attempt to simplify the complex. Today I want to talk to you about light. So what is light? Light is a boson, right? So boson is kind of like the opposite of a fermion, right? When we talk about fermions, they cannot have exactly the same quantum states, right? The Pauli exclusion principle applies to fermions. Well, light is not a fermion, it's a boson. Bosons can have exactly the same quantum states. So they can be packed on top of each other to make a bigger group of them, right? There's no limitation, as far as we know, as to how much light you can stick in one packet, right? On here, a representation of the longitudinal wave, which is the magnetic field and the electric field. So using the right-hand rule, if I take the electric field and I cross it with the magnetic field, I get the direction of motion of my photon, making the magnetic field always perpendicular to the electric field and perpendicular to the direction of motion. So it's a longitudinal wave because the magnetic field and the electric field both will oscillate perpendicular to the direction of motion, right? So imagine these things are both oscillating, right? And that motion is this direction. So the photon is traveling in this direction, which I'm calling x. So this equation describes the magnetic field as a function of x and t. This one describes the electric field as a function of x and t. This is a form of electromagnetic radiation, right? So it's an electromagnetic wave. The frequency of this will allow it to range anywhere from visible light to radio waves, from microwaves that cook your food, right? All of that is contained within this structure. So I have, again, a magnetic field, which is writing. It is described as this function. So I have some maximum, right? So at some peak times cosine, because this is a cosine wave. This is the spatial component. This is the time component. So imagine this describing if I froze the wave in time, how I could look at it as a snapshot. This would be an example, right? So if I just froze the wave in time and I just looked at it spatially, that's what it would look like, right? If I just got rid of this time term. If I got rid of the space term, I'd be looking at it as just time, right? So I'd be seeing, hey, how is this, if I had a point as the wave passes in time, how is it described? That's here, okay? Same thing with the electric field. And again, we need both the electric field and the magnetic field to give us all of the properties that allow us to use all these devices that we have created, right? It will also help us with understanding what happens to this wave when it is absorbed by something, an electron absorbed by a nucleon, something along those lines. So it will help us understand all of that. Talk about some pieces here. So this lambda, what is lambda? Lambda is the wavelength. What is a wavelength? It is the length. Again, this is a snapshot, right, of what the wave would look like at some instant of time. The distance of one cycle, right? The distance of one cycle is the wavelength. This is the fundamental cycle that is repeating. If I took it to here, that is also repeating, but it's not the fundamental cycle, right? So the fundamental cycle is here. That gives me my wavelength. So that's the term that goes here, is this wavelength. This wave is going to travel at some speed. That speed is going to be the speed of light if it's in a vacuum, right? But if there's molecules in the way, then it will slow down the wave as it's passing through. And if it slows it down, it's going to have unique effects, which we'll talk about that too. The time term, right? This nu, this is the Greek symbol nu. You could have also put F, right? So nu is equal to speed divided by the wavelength, which is also equal to the frequency F, right? So this is the frequency, How much energy is traveling? That's important for us, right? So we have this thing called a Planck's constant. So Planck theorized that if I took the energy of the photon and I divided it by the frequency of that photon, that would be some constant value. Turns out it to be true. So Planck's constant is a constant. I can find the energy of this wave if I know the frequency. So the energy is equal to Planck's constant times the frequency, which is also equal to, again using this relationship, the speed divided by the wavelength. Speed divided by wavelength. So Planck's constant times speed divided by wavelength. So if I know the wavelength, or if I know the frequency, then I know the energy. If I know the energy, then I know the frequency, and I know the wavelength, given that we're talking about in a vacuum or near vacuum, so that the speed is constant, speed of light. Listed here a useful set of constants that I would write down somewhere so that you have them readily available whenever you need to solve a mathematical problem related to photons. Speed of light in a vacuum, right, is c. This is the theoretical limit to all speed anywhere. It is about 3 times 10 to the 8 meters per second. Planck's constant, right? Planck's constant is 6.626 times 10 to the minus 34. This is kilograms meters squared per second. So kilograms meters squared per second. A joule is a kilogram meter squared per second squared. That means this quantity is kilograms meters squared per second squared multiplied by seconds. That makes this joule seconds. So that means that I have Planck's constant in a form of energy times time, which is helpful when I'm trying to solve equations. Okay, so this is joule seconds, but I may not always want to use joules. A joule is kind of a big number, so maybe I want to use electron volts. So here I have the equation in electron volts, which is just another form of energy. Electron volts seconds. And to get from electron volts to mega electron, I have 10 to the 6 electron volts in 1 mega electron volt, or I have 10 to the minus 6 mega electron volts in 1 electron volt, depending on how I want to look at it. But if I take this quantity in electron volts, multiply it by 10 to the 6, I end up with mega electron volts. I have Planck's constant times the speed of light. So Planck's constant times the speed of light. Both of these are constants. So both of these are constants, which means that I can have a constant quantity, right? Constant times a constant is a constant. This is in kilograms meters cubed per second squared, right? So kilograms meters cubed per second squared. That is a kilogram meter squared per second squared multiplied by meters, which gives me joule meters, right? So joule meters. Convert this into electron volt meters. Gives us this quantity. And so I have 10 to the minus 6. It might be useful for me to use micro. So I have 1.240 micro electron volt meters. So now let's talk about what happens when light interacts with matter. So here I have a photon, a single photon. Remember we said that photon energy is equal to Planck's constant times the frequency. The photon also has some momentum, right, that's carrying the wave. That momentum is Planck's constant divided by the wavelength. Remember we had our relationship that the frequency is equal to the speed divided by the wavelength. So I have this photon, a single photon. It's going to interact with a single electron. Now there's also a possibility there's no interaction at all, but in this case there is an interaction. So this is a case where I have a single photon interacting with a single electron. What could happen to the photon? So the photon could just bounce off, keeping its energy, keeping its momentum. If that happens, we call that elastic scattering. So if it elastically scatters, then the photon of 2 equals the photon of 1. The frequency did not change, right? So the frequency of 2 equals the frequency of 1. The wavelength didn't change, so the wavelength of 2 equals the wavelength of 1. No energy was given from the photon to the electron. All energy was maintained in the photon. This is called elastic scattering. We can have absorption, right? So all of the energy of the photon could be absorbed in some way by this electron. That could happen. If that happened, we call it absorption. There is no second photon. So now for the weird one, inelastic scattering. In the case of inelastic scattering, the photon interacts with the electron, giving it some of its energy and momentum. So now I have less energy and momentum on the photon that is emitted. Okay, so photon 1 is now gone. I now have photon 2. Okay, so photon 2 is going to have less energy than photon 1. It's also going to have less momentum than photon 1. This new photon, photon 2, is a different photon. Okay, photon 2 has less energy and less momentum. Because it has less energy, the frequency of our new photon has to be smaller, right? If I have less energy, if the energy went down, Planck's constant is a constant, therefore the frequency must have gone down. Since the frequency went down, I have a lower frequency on photon 2 than I have on photon 1. Momentum also given away, right? So it lost the momentum. Inversely proportional. So if the momentum goes down, then the wavelength goes up. So my new photon, photon 2, is going to have a longer wavelength than photon 1. This is still true, right? The frequency is still inversely proportional to the wavelength. My new photon, photon 2, from my inelastic scattering, is going to have a lower frequency and a longer wavelength. All right, so now I'd like to talk about how we can create photons. So how are photons created? I got 3 cases on the board here of ways that photons can be created. I can have de-excitation. So if I have a bound system of fermions, for example, an atom, the fermions can get excited, right? They can go from a lower energy state or the ground state to some excitation state, to some higher energy state. Well, that's unstable, and eventually it will decay back down to the ground state. When that happens, right, when I go from a higher energy level to a lower energy level, one of the things that can happen is the creation of a photon. So the de-excitation of a bound fermion can cause the creation of a photon. These are very characteristic and can be used to classify, for example, stars, right? You can see what materials are in a star based on what light is emitted from it, because it's characteristic of individual atoms. We can have pair annihilation. So if I have matter and antimatter, right? So in this case, I have an electron and a positron. So if an electron and a positron touch, they will annihilate. In this annihilation, they will create 2 photons. Got to have at least 2 photons because you have to conserve momentum. You can't conserve momentum if you only create 1 photon here. So you have to create at least 2 photons in order to conserve momentum. And finally, we'll talk about acceleration, de-acceleration of a charged particle. So what I have here is an electric field, all right? So some electric field, and I've got a free electron that is in that field. by either accelerating it or decelerating it, there will be a net loss of energy from the system. That loss of energy is the creation of this photon. Something I didn't really stress earlier is photons come in many different frequencies. Okay, they can be in X-rays, they can be gamma rays, right? That's more of these productions. These are like the X-ray gamma rays. This will be gamma rays, okay? This is how you get radio, right? Radio waves transmitted is you accelerate and decelerate in a cyclic fashion a free electron from like copper wire, and it will create radio waves that you can use to transmit information. As I mentioned, light is a wave. So property of waves is that you can add them. Okay, so let's say I have a wave and I want to add another wave to it. Okay, so if I had A cosine B and I add the same thing, A cosine B, I will have the same frequency, but I'll have a bigger peak, right? So if this was the electric field or the magnetic field, and I added both of them together, I would have double the electric field or magnetic field that I had from each individual light wave, right? I could have complete destructive interference, so this would be constructive interference, complete destructive interference. So if I have exactly the opposite wave that I start with, so let's say I have this light and I shift the phase by 180 degrees, then if I add those together, I'll completely negate the wave, right? So I completely cancel that wave out. If I have some other thing, right, so some other wave that I add in there, then they will add together to give me some other wave. All right, so now let's talk about diffraction. So let's say I have a beam of photons, right? So we've engineered this such that I have a set of photons all going in exactly the same direction and all having the same wavelengths as they are traveling this direction. So I have parallel wave fronts, right, of a beam of photons as they are traveling towards a slit. So I try to represent the individual photons once we get near that slit. The wave nature of these photons is going to cause it to bend around, much like a river. If you have a rock in the middle of a stream, you'll see that the waves of the water will bend around that rock. Similar here, right? The wave nature of this light means that when these perfectly aligned photons hit this slit, they bend around the slit. So now I have different wave fronts. To start off with everything parallel, now I have these curvature wave fronts as I go through the slit. Now this of course means the slit has to be small, but for a slit size that approaches the wavelength of the photon that is coming at it, we will have this bending of the light around the gap, okay? So imagine these individual photons, they bend in different directions and they have wave fronts for these individual sets of photons. We can see that we have some of them will constructively interfere and some of them will destructively interfere as they are traveling. Well, if I put a wall, right, or a plane of some sort at a distance that is pretty far away compared to the size of this hole, then I will see patterns on the wall that will be dependent on the size of the hole and the wavelength of the light. So here is a graph of what kind of intensity I would see, right? So imagine bright, bright, bright in the middle. That makes sense. But these dark parts here, that can only happen because of the destructive interference. As we just talked about, when two waves exactly overlap, you get a null, and that's what we see here when we have this single slit experiment, that I will have destructive interference, which will cause dark spots. Then I have follow-on constructive interference, which gives me a secondary bright spot. So of course, you're going to get more of your photons coming through the center. Less will bend than just travel through. So you're going to get more intensity directly in front of the hole. But if I did not have the wave nature of the photon, then I would not be able to get this destructive followed by constructive followed by destructive interference patterns. All right, let's talk about what happens to our photons when they enter a medium. So let's say we have a number of photons. They're going to enter some semi-transparent or transparent medium and then emerge on the other side. So when they go into this medium, now we have molecules. So here we had a vacuum, here we have a vacuum. But in here we have molecules of something. Could be glass, could be water, something. We have molecules of something. Well, we just talked about several interactions that occur when photons interact with matter. Okay, I could have diffraction, right? So if the molecular spacing is at just the right distance, you could have diffraction around those molecules. That will be happening in there. We will have absorption and emission, right? So some of the electrons will absorb the photons and re-emit them, okay? That will happen throughout this medium. You'll have interference. So from the diffraction and the absorption and emission, you will have interference within those. So you will have some phase shifts as we interact. We'll have elastic and inelastic scattering that will occur throughout the medium. All of this has an effect of slowing down the speed at which light travels, at least as a group, through the medium. So on this side, I have vacuum. This side, I have vacuum. As I travel through, the speed inside the medium will be lower than the speed of light. However, some of that light has to be absorbed by the medium, right? So I have to have less photons out than I have going in because some of them will interact, raising the overall entropy of the system. Thank you for watching my video. Please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.